Aloha and welcome to our video on dating with radioactivity. In this video, we'll describe what radioactivity is in a half-life, we'll explain what radiometric dating is, we'll describe how carbon-14 is used in radiometric dating, and finally we'll explain how radiometric dating of igneous rock layers can help date sedimentary rock layers indirectly. Okay, so to get started, we should talk a little bit about nuclear decay. In nuclear decay, what we're talking about is a radioactive atom, and that radioactive atom is going to have an unstable nucleus. So that nucleus is going to undergo nuclear decay until it can form a stable nucleus, and oftentimes that'll be a different element. So in our example here, we have iodine, and iodine is going to be radioactive, and it's going to decay down into xenon. Now iodine is going to be the parent element, that means that's what we're starting with, and it's going to form the daughter product. So we can kind of do that. One of the interesting things is this nuclear decay happens over certain rates, and it goes by half-lives. And a half-life is where half the original sample is going to decay down to the daughter product. So if we look here, we start off with all parent sample here. After one half-life, we're at half parent here and half daughter there. We go through another half-life and we cut whatever we had in half, so now we have a quarter, and we'll have 3/4 daughter, and after 3 we'll have an 1/8. And that helps us because we can look at that ratio from parent element to daughter product, and that's how we do radiometric dating. So taking a look at this chart from the lessons, you can see that we have our radioactive parent and then we have our stable daughter product. And then we can get some ideas here of half-lives. So uranium-238 is going to decay down into lead-206, and it takes about 4.5 billion years for this to happen, and that's about the age of the Earth. So that means any of the uranium-238 that was around, we now have half as much. Half of it has decayed down into this lead-206. And you can see some of the other ones here as well. We have uranium-235, we have thorium-232, potassium-40, and these are all different radioactive isotopes that we use for some of this radiometric dating. Now, perhaps the most common one that you've heard of is using this carbon-14 dating here. And carbon-14 is kind of interesting. What we'll have is we have this nitrogen-14 that's out in the atmosphere, and we have cosmic radiation. So gamma radiation from the sun is going to cause neutron capture, and that's what's going to form this carbon-14. Now, carbon-14 is going to be taken in by animals through breathing, through eating, all of that kind of stuff. And then once it dies, we no longer have this, and we start seeing that carbon-14 break back down into nitrogen-14. So we can take organic material that had this carbon incorporated into it, and we can use that to find out how old or how long ago those things passed away. And carbon-14 is going to get us back to about 50,000 years or so. So it gives us a more recent way of measuring the ages of like remains and things of that nature. Now, radiometric dating can work when we're using like igneous materials and when we're using things of that nature, metamorphic materials, but it doesn't work so well when we're talking about sedimentary rocks. And the reason for that is sedimentary rocks are made up of sediment, and that sediment is going to have been eroded away. So we can have some igneous rocks that we can date radiometrically, but then they break away and then they form into this sedimentary rock, and we don't know when that sedimentary process happened. So what we can do is we can use a lot of times, we can use inclusions and intrusions of igneous materials, and that'll give us the ability to kind of roughly date these sedimentary rocks. So if we notice here we have a volcanic ash bed that was 160 million years, we know that these are going to be older than that, and everything above it is going to be younger than that. And if we have this intrusion here at 66 million, then we know this Wasatch on top is going to be younger than 66 million, but we know that these here are going to be older than that 66 million years. Okay, so that's the end of our video. As always, the lessons will go into a lot more detail. I just wanted to give you a quick introduction. Good luck on your quiz, and we'll see you in the next video.